In today's notes, we're going to look at sequences, series, and summations. If you think back to the notes from last class, we talked about an introduction to sequences and series. That document mainly focused a lot more on just sequences, and we didn't really touch too much on series. On this page, we'll actually talk about each of those and describe in good detail how they represent the different items that we're looking for. So for the first part, look at the items below. So if you look at the list below, the list of numbers, these are often called a sequence. We talked about this last class period. In a sequence, we're looking for a specific pattern. How are we getting from one number to the next and to the next number? Those can either be finite or infinite. And we also talked about how to write their explicit formula or their explicit rule, which is kind of like a general rule. We always note these by a sub n, like we see here. So a with the subscript of n for some number. The only new thing is this row, which is talking about converge and diverge. Whenever you're converging, that's when you're trying to get closer and closer to one specific number. We're going to see that on a few questions today. Diverge is when you're not getting close to a specific number. So the numbers are not really following any specific pattern, or not any specific pattern, but they're not getting close to a specific number. That's what I mean. So let's go ahead and define converge up here. When you're converging, you are getting closer and closer to not just a, but one specific number or value. So that's when you're getting closer and closer to one specific value. So for some of the questions that we see today, we're going to get close to one specific value. Okay, let's look at the first question. So in this first question, we have the following numbers: 1, 3, 5, 7, 9, and 11. So those are all the numbers in our sequence. So we're trying to figure out, okay, what is a sub 1? Okay, well, a sub 1, if we look at the numbers we have here, you should define it as literally the first number. If it makes it easier for you, which it usually makes it easier for me, I'm going to make a small little table over here to the side for n and a sub n. All of these values are a sub n. So I'm going to list all of those in this table. And all of the n values, if you think back to an introduction to sequences and series, this is when we talked about using n is going to be representative of just one. You start with 1 and you pretty much keep going from there. So 1, 2, 3, 4, 5, and 6. So if I'm looking at a sub 1, which is literally the first one, that's going to give me positive 1. A sub 2 is positive 3. And a sub 13, well, we need to find the general form first before we can actually write a sub 13. So remember, that general form is your explicit form or explicit rule, which is going to be representative of a sub n. So how are we going to get for any value n? How are we going to get to that number? Okay, so let's look at the a sub n column. We know that to go from 1 to 3, we have to add 2. 3 to 5, we have to add another 2, and so on. It just so happens that each of these, if you add 2, you'll get to the next number. Usually the n column isn't too helpful, especially for some of these questions. It might be, but it isn't necessarily always going to be helpful. All of these numbers of adding 2 is helpful, though. If you think back to the last page, we said whenever you have a repeated addition, what do we have? If you have a repeated addition, what are you supposed to do? Well, if you have a repeated addition, you're supposed to be multiplying. So we're going to take that value, 2, which we're adding repeatedly, and we're going to turn it into multiplication. That's kind of like your hint. So for this one, we're going to have 2 times n. So let's kind of confirm that that's what's going to happen. If we multiply 2 times 1, we should be getting 2 here. And for instance, if we were to add 2 times 2, we should be getting 3 here. Okay, I'm missing something on this a sub n. If I do 2 times 1, that'll give me 2. In order to get 1, though, I need to subtract 1. Same thing here. If I have 2, which is 2 times 2 will give me 4, 4 minus 1 will give me 3, and so on. So check the rest of them, make sure it works, and you should see that it does. The last thing we're going to do is find a sub 13. So we're going to take that n value of 13, plug it in, and subtract 1. So 2 times 13 is going to be 26. 26 minus 1 is 25. The last part here is asking, does this converge or diverge? Okay, well, with this little space that I have here, I'm going to draw a rough sketch of my graph. Here's my x-axis, here's my y-axis, or my bad, let me rewrite that with my variables that I have. N axis, and here's your a sub n axis. Okay, well, we're going to roughly graph them. So we're going to say 1, 1 is here. 2, 3 is about here. 4, 3, 5 is here. 4, 7 is here. 5, 9, and then 6, 11. So these numbers they're going to keep going up. If we look at these, are they going to a specific number like 1 or 2 or 3 or maybe even 15, like up here, 15? Is that going to keep going and maybe get to that? Well, if you look at a sub 13 here, it's getting to 25. None of these numbers are getting close to one specific number, like 1. These numbers in this sequence are getting close to infinity. It's not stopping anytime soon. So for this question here, I'm going to circle diverge. This is going to diverge to no specific value. Let's look at the middle one. The middle one is a little different, so make sure that you have your brain with you. And we're going to go ahead and try to figure out what these numbers are going to look like. So for this first question here, we have 0 over 1, 1/2, 2/3, 3/4, 4/5, and 5/6. Okay, with this space that I have, I'm going to make a small little chart. I'm only going to be able to put up to 5 for this one. Actually, you know what? I can put the last one. And we're trying to figure out a pattern. So take a second and look at each of these. What kind of pattern do you notice? Okay, well, if you take a look and actually see each of these, the n value is actually the same as every denominator. The n value is the same as every denominator that I have. Okay, so that's good. So that's going to help me with identifying my nth term. Look at the numerators, though. What's going on in the numerators? Okay, well, we know that it's not the exact same value as n, because n is already your denominator, but it looks like if maybe we subtract 1 from the numerator, or subtract 1 from n, we'll usually get that numerator. So for instance, we have 2 in the denominator, 2 minus 1 is 1. We have 3 in the denominator, 3 minus 1 is 2. So it looks like our numerator is going to be n minus 1 over n, because every n value that we have, we're going to subtract 1, and then that's our numerator, and then just the n value itself will be our denominator. Okay, I got ahead of myself, but I want you guys to definitely label A1 and A2, which in this case are going to be 0 over 1, which is just 0 and 1/2. For A sub 54, we're going to plug in 54 here and here to get our answer. So I'm going to make this 54 minus 1 over 54. Well, 54 minus 1 is going to be 53 over 54. That's my answer. Okay, so let's answer the last question that we have. The last question that we have is, does this converge to one specific number, or does it diverge? Does it kind of not go to a specific value, but usually it'll go to like positive or negative infinity, just depending. Okay, so let's take a second and look at all the numbers. I'm going to remove this 0 over 1 just for a second, because that 0 over 1 was really just helpful for my pattern. And let's look at the actual numbers that I have. Okay, well, 0 is just 0. 1/2 is 0.5 as a decimal. 2/3 is about 0.6 repeating as a decimal. 3/4 is about 0.75. 4/5 is about 0.8. And 5/6 is about 0.83 repeating. Well, these numbers definitely look like they're getting close to something. Let's go ahead and graph this out, just a very rough sketch. Here's my n, here's my a sub n axis. Okay, so 1, 0 is about here. 2 and 1/2 is about here. 3 and 2/3 is a little bit bigger. 4 and 3/4, that's 0.75. If we were to keep going, those values aren't really increasing per se. They're kind of starting to level off a bit, because we notice from 0 to 0.5 that goes up by 0.5, but going from 0.5 to 0.6, that's not going up as much. These look like they're getting close to 1. This is starting to kind of curve off. This is acting as an asymptote. So if you need to, think of converging as kind of approaching an asymptote, where it's going to get close to, but never actually touch. So for this question here, this graph is converging. These points, this sequence is converging, and it's converging to 1. So make sure you not just write out converge, but you also say where it's converging to, what number, what specific value. Trying to erase these two little hashes. And let's go ahead and look at number 3. For number 3, they've already given you the sequence, the explicit form. They've given it right here, but they didn't give you the sequence of values. So let's go ahead and find maybe like the first 5 numbers or so that'll give us the first 5 values of this sequence. So go ahead, start this off, create a table if I were you. So go ahead and pause the video, start this off. What is it going to look like? So I have my n, and I have my a sub n. So for 1, I'm going to plug in 1, -3 to the first power. That's going to give me just -3. So that's my first value in my sequence. For 2, we're going to do -3 squared. Well, -3 squared is positive 9. 3, we're going to have -3 to the third power, and that's going to give me, well, -3 times -3 is positive 9. Positive 9 times another -3 is -27. For my fourth term, we're going to do -3 to the fourth power. So we're just going to pretty much take that -27 and multiply it by another -3, which will give me an 81, positive 81. And then for my last one, let's do -3 to the fifth power, and that's going to give me -243. I'm going to keep putting dots behind it just to show that I'm not going to necessarily stop at -243, but that's pretty much the highest value I'm going to go to for now. Okay, well, a sub 1 is going to be -3, a sub 2 is 9, and a sub 100 is going to be -3 to the 100th power. Okay, well, let's be honest. Even if you did have a calculator, it's going to be a really big number, really, really big, because you're multiplying -3 100 times. Based on the pattern that you guys hopefully have already noticed, when you have odd numbers that you're finding, your answer is going to be negative. For all of the evens, so for 2 and 4, these are both positive. So I do know since 100 is even, I know that the answer is probably going to be a positive 3 raised to the 100 power. I just don't know what that is. So on tests and quizzes, especially if I don't give you, especially if I give you a value this large, just leave it in its exponential form. And I'll hopefully put that in your directions as well, when it's okay to leave in its exponential type form or in its non-simplified form. The exact form, that's what I'm trying to say, your exact form. Okay, now we need to figure out, is this converging or diverging? So in this part of your graph that you have, or in this part of your paper, let's create a graph. This is my n axis, this is my a sub n axis. Okay, let's think. We have 1, -3, that's down here. 2, positive 9 is somewhere up here, so it's kind of going up. 3, -27, we'll say is down here. And then 4, positive 81 is somewhere, we'll say up here. And then 5, -243, we'll say is down here. And it looks like, based on this pattern, it's probably going to keep going up, and then back down, and then back up. And it's just going to keep going on and on forever. It's not going to stop. Is this converging or diverging? This is diverging. It's not getting close to any specific value, one specific value. This top part is getting close to infinity. This bottom part is getting close to negative infinity. So it's not getting close to one specific value. It's getting close to a lot of different values. So right now, these 3 questions at the bottom, I want you right now to pause the video and do these 3 questions. Go. So, as you can see, I've worked all of them out, except for the last one. For the first 2 questions, pause the video if you need to, check your work, make sure it looks good. And if you notice that any of those questions don't look the same as what you've gotten on your paper from what I have on my paper right now, check my paper later. So check your questions right now. Make sure they look like the answers that I have on my paper. If they don't look like the answers that I have on my paper, I am going to post up my answer key worked out with all of my things onto our class website soon. So just be patient and wait for that later. For the last question, though, I haven't started, but I haven't finished it. And I think it's a good time for me to kind of go through it to make sure you understand what you're supposed to do. So for this last question, the main thing that I need to find now is my general form, the explicit form for this. Okay, so in order to find the explicit form, let's just take a second and look at the pattern that I'm noticing. So I have all of these items here from 100 to 0.01, and it looks like every single time that we're going from one value to the next, it looks like it's literally losing a zero. So literally, if I'm going from the first one to the second one, I literally just cross out a zero. If I'm going from the second one to the third one, I cross out another zero, and so on. Technically for 4, from 3 to 4, if I'm starting at 1, well, I would need to move the decimal place 1 unit to the left in order to get 0.1. And it's just going to keep going from there. So what I need to find out is what's the pattern. Okay, well, it looks like for this pattern, it looks like you're taking off 10 every single time. You're dividing it by 10. So whenever you're crossing out that 0, that's pretty much dividing it by 10. So I'm going to put here that I'm going to make 1 over 10 to the nth power. Every single time, I need to divide it by 10. Based on what I currently have, with this 1 over 10 to the nth power, it's not going to give me negative 100 if I plug in 1 here. So definitely do that. 1/10 to the first power is just 1/10. It's not going to give me negative 100. So in order to get negative 100 for this first term, I'm going to have to multiply the whole fraction, 1 over 10 to the nth power, times 1,000. By multiplying it by that 1,000, I'll be able to pretty much get that negative 100 because this 0 will go away when I divide it by 10. So that's definitely what I want. The only other thing that I notice is that as I go from one to the next, it's going from negative to positive, negative to positive. For all of these questions, it's fluctuating between negative and positive. So anytime you're trying to go between negative and positive values, what you're going to do is you're going to rewrite it as negative 1 to the nth power. Every single time you plug in one of those n's, you're going to get either a positive or a negative 1. So for instance, negative 1 to the first power is going to give me a negative answer. Negative 1 to the second power is going to give me a positive answer because negative 1 squared is negative 1 times negative 1, which is positive. And we can keep doing that for all of these questions. So this is my general form. This is my explicit rule. There's technically multiple other ways that you could write this. I'm going to just show you 2 more ways that you can write it in this space up here to the side. So one of the other ways that you can write this is if you were to take the 2 fractions or the 2 numbers that are in parentheses and multiply them. So literally if you just multiply that out first, then you can get your answer and it should be the exact same. So you would get negative 1 over 10 to the nth power. That would be another way that you could write this. The last way that you could write this kind of requires you to think back to Algebra 1. 1,000, which is this guy here, is the same thing as 10 to the third power. If I was to have 10 to the third power and divide it by 10 to the nth power, because remember, every time that I do one of my expressions from one to the next, I'm going to take off a 0. So that's 10 to the nth power. If I have my answer looking like this, what can I do with the exponents? I have 3 and n. Well, if you think back to Algebra 1, when you have the same base, you can just take those exponents and subtract it. So here's your last way that you could write it. You could rewrite it as 10 to the third power minus n times negative 1 to the nth power, because you want to make sure that you note that the values are going to keep switching from positive to negative. There are probably a couple of other ways that you could write this, but these are the 3 most common ways that I usually see students write that. For the last thing we need to identify is the converge and diverge. Okay, well, I need to figure out based on my graph, let me graph this out, what's going to happen here. So we have a sub n and we have n. Okay, so let's think of the graph itself. If I start with negative 1, negative 100, that's going to be somewhere down here. 2 and 10 is up here, so I'm going to have this go up. And then 3, negative 1 is going to be somewhere down here. 4.1 was going to be up here. 5, negative 0.1 is going to be somewhere down here. And then it's going to keep going. It's literally just going to keep going just like this. Is this converging or diverging? As you notice, every time it loses a 0, it's actually getting closer. Even though the values are fluctuating between positive and negative, this is converging. What is it converging to, though? This is converging to 0, which is the x-axis. This is converging to 0. If I was to keep going with this pattern, it's going to get so small that it's pretty much just going to be the x-axis. It's literally going to look just like that. So that's your answer. Let's go ahead and take a second and look at the next section. In this next section, we're going to write the first 4 terms for your sequence. This is very similar to what we did last class period in our intro notes. So let's go ahead and finish this up. For question number 1, if I'm writing the first 4 terms, I'm going to start out by putting 2 in the first spot because a sub 1 is going to be 2. And this is a comma, by the way. That's a comma. Okay, let me find a sub 2. Well, in order to find a sub 2, I'm going to have to take 4 times a sub 2 minus 1 and then subtract it from 3. Well, a sub 2 minus 1 is going to give me 4a sub 1 minus 3. So we just need to take that a sub 1 value and plug it in. So 4 times 2 minus 3. 4 times 2 is going to give me 8, and 8 minus 3 is going to give me 5. That's my first value for a sub 2. For a sub 3, I'm going to do the same thing. So for a sub 3, I'm going to make this 4a sub 3 minus 1 minus 3. So we're going to make this a sub 3 is going to equal 4 times, I don't know why I keep putting that in parentheses, we're going to make that a sub 2 minus 3. So 4 times, in this case, a sub 2 was 5. We just found that. We'll subtract 3. So if I was to subtract, a sub 3 is going to give me 4 times 5, which is 20. And 20 minus 3 is going to give me 17. That's my third value. For a sub 4, last part, we're going to make this 4 times a sub 4 minus 1, which is going to turn into a sub 3 minus 3. Well, a sub 3 is going to be 17 because we just found that. So 4 times 17 minus 3. 4 times 17 is going to give you a pretty big number. Let's see, 4 times 17, that's going to give you 68. And then 68 minus 3 is going to give you 65. So a sub 4 is going to give me 65. Right now, you pause the video and do number 3. Give me the first 4 numbers in my sequence. Remember, a sub 1 down here, that's your first term. So I'm literally going to put 1 as my first value. The next one should have been 2, and then 6, and then 24. Those are your first 4 terms. So in the last part that we're going to talk about at the bottom of this page, it says a blank is the sum of all of the terms of a sequence. This is called a series. So a series is the sum of all of the terms of a sequence. That literally means you just add everything together. That's a series. So the sequence 12, 15, 18, and 21 would have the corresponding series of, okay, well, we got to add all of those numbers. So literally add 12 plus 15 plus 18 plus 21. Add all of them up, and that would be your series. Well, the series for this one, if you add all of those, is going to be 66. That's your answer. To help us write the series compactly, we use what's called summation notation. Summation notation pretty much prevents us from having to write out all of those values. We just write it as one little summation symbol, and that tells us what we're supposed to be adding. So in this little notation that's represented below, we're going to show how we would take the first n terms and add them. So in this notation, we're going to have your summation symbol, which is representative of this little e, and then you have the I on the bottom and the n on top. So I, in this case, is called the index of summation. The index of summation is what you're starting with. So this little I down here, and usually also it can have an n or a k, it can have any variable. That number specifically tells you what you're starting with. So in this case, we would be starting with 1. From there, the n at the top is called your upper bound or your upper limit. Your upper bound / limit. That's going to help you with actually going to the top. Okay, so what is the highest value you can get to? So for instance, if there was an 8 here, we would just go to a to the a sub n power. That's all we would do, or a sub n notation. So the n is your upper bound, which means that the 1 down here with I is called your lower bound or your lower limit. That's an R, bound or limit. There's two different types of series that we can have. The first type of series is called a finite series. And that series is when you have the sum of the first n terms of a sequence, and that's only just to n. So whatever n represents, you're just taking the sum of those first n terms. This is called a partial sum. Hopefully I spelled partial right. I didn't. P-A-R-T. Partial sum. So you're only taking part of it. If we were to continue and go to infinity, that means we would cover all of the different types of your sum. But if it's just going up to n, it's considered a partial sum. For the last question, a infinite, so an infinite series is the sum of all of your terms, and it continues for the entire sequence. So it wouldn't stop at any value. It would literally just keep going. So I'm going to give you an example down here at the very bottom. You actually have space on your screen or on your paper, but on my screen, if I was to start writing down here, you wouldn't see it. So for me, I'm going to do it on a new page, but you guys actually have enough space to continue your answer down here at the bottom. So you continue on that page. I'm going to put it over here. To find the number of terms in a series, there's two ways you can do this. So to find the number of terms in a series, what you're going to do, for instance, if we had the summation of 5i is equal to 2, and let's say we had 3i, what you would do is you would write this out as 3 times 2 plus 3 times 3, because remember, we're just literally starting with here, 2, and we're plugging this in for I. So after you start with 2, just keep going numerically. Plus 3 times 4 plus 3 times 5. Should I put 3 times 6? Since the upper bound is 5, that tells you where to stop. So since the last part is 5, that's what we're stopping with. How many terms do we have here? Because remember, the problem says to find the number of terms in a series, this is what you do. 1, 2, 3, 4. This one has 4 terms. Let's say this number at the very top was like 100 instead of 5. I wouldn't expect you to write out 100 this many times. It wouldn't make sense. So instead of doing that, what you can do instead is you can do this formula. Then this formula is the upper bound minus your lower bound. After you subtract both of those, just add 1. So for instance, if we had an upper bound for this question, your upper bound is 5. I would subtract it from 2, and then I would add 1. 5 minus 2 is going to give me 3, and 3 plus 1 is going to give me 4, the same 4 terms. Instead of having to write it out, we can just find it this way. So it'll give you the same 4 terms. Okay, so that wraps up the items on the very first page. To find the number of terms in the series, which is what we just did, that's this information that you should be putting at the bottom of this page. So I've literally just answered this question on that page that I just did. Right now, we're going to look at a few questions on the last page. So let's flip this over. Okay, so on this last page, we're going to do a couple. I've already kind of done number 4, so let's look at number 5. This one specifically says to rewrite each as a sum. So I'm not going to actually find the answer. I'm just going to rewrite it as a sum. So what would I be adding together? So for question number 5, I would take P, which in this case, remember, this is like your I. This is where you're starting with. That's your lower limit. This is my upper limit, or my upper bound and lower bound. So for this question, I'm going to rewrite this as 1 to the first power plus 2 to the second power, 3 to the third power, 4 to the fourth power. Do not keep going because 4 is your highest value. This would be your sum. Remember, this problem just said to rewrite what you would look like as a sum. Right now, you guys do question number 6. Rewrite this as a partial sum, because technically this is a partial sum. You would rewrite this as, let me make sure I have enough space. We're going to start with, I don't need a bracket. We're going to do 7 times 7 plus 3 plus 8 times 8 plus 3, 9 times 9 plus 3, 10 times 10 plus 3. That would be your sum. You can put the brackets around it, around each of the terms, but it kind of can get a little exaggerated if you kind of do that. But I do understand, because even on my key, I put the brackets around it. You don't have to, because technically after you add those things in the parentheses, you're going to multiply by the number directly in front. Okay, for the next 2 questions at the bottom, let's look at numbers 8 and 9. For question number 8, it says for you to actually find the sum this time. So we're actually going to calculate what the sum is. Okay, for this first question, number 8, we're finding really just a partial sum. We're not finding the whole thing. We're just finding a small piece of it between 1 and 3, because 3 is your upper bound, 1 is your lower bound. Okay, so let me find this out. I'm going to write this answer the best that I can. So I'm going to put it as 3, 10 to the first power, 3, 10 to the second power, and then 3, 10 to the third power. That's technically what we're adding. Okay, well, it looks like we can definitely add them. If I was to write this out, I could do this as a fraction. Let me go ahead and do this as a decimal. If I was to write this out, I have 3 over 10 plus 3 over 100 plus 3 over 1,000. As a decimal, I could actually write these out pretty easy. 3 over 10 is just 0.3. I would add that to 3 over 100, which is 0.03. And then 3 over 1,000 is 0.003. So there's 2 ways I'm going to write my answer. I'm going to write my answer as a decimal and as a fraction to show how to write it both ways. And on your tests and quizzes, you'll be able to probably do the same thing. Just make sure you read the directions. So for this question, my decimal is going to be 0.333. Don't put in a repeating symbol, because we're not going to keep this going. This literally ends at 3. So we're just putting those first 3 terms. This is my decimal answer. The only other thing I would probably do is write this as a fraction. Well, if I write this as a fraction, I have, let me see, there's 1, 2, 3 decimal places. I can write this as 333 over 1,000. This is my simplified fraction answer. So those are my 2 ways that I could write this. You don't literally have to sit there and find a common denominator for all of these. If you do, that will give you your fraction answer first, and you're still going to have to find it as a decimal. So both of these ways will get you the same answer. I will make a note for questions 9 and 11. Both of those symbols are infinities. So at the top, both of these symbols are an infinity. So let's go ahead and look at number 9. So for question number 9, this says we're going from 1 to infinity. Okay, guys, let's go from 1 to infinity. So we're going to go 3 over 10 to the first power, 3 over 10 to the second power, 10 to the third, 3, 10 to the fourth, 10 to the fifth, and I would literally just keep going. Literally just keep going. Let me write out what the decimals are going to look like and then see what's going to happen. So this would be 0.3, 0.03, 0.003. I think I put too many zeros for that one. 003, 0.00003. And remember, this can keep going. This is what it would look like if you had a repeated decimal, because if you were to add up all of those, you would get 0.33333 repeating. So in order just to write that simply as a decimal, I would just put 0.3 repeating. That's your decimal answer. What would that look like as a fraction? As a fraction, 0.3 repeating, you should know that from the beginning part of Algebra 1 and even middle school math. This is just 1/3. That's my fraction. So right now, you guys are going to pause the video, and I want you to find the fraction for number 10 and the decimal for number 11. So right now, pause the video and find both of those answers. For question 10, I have all of the work posted on your class website, so just be patient, check it later if you need to. But your fraction answer for this question should have been 555 over 1,000. And the decimal answer for question 11 should have been 0.5 repeating. So 0.5 repeating for number 11. All right, we're almost done, guys. Let's look at the last couple of questions. For question number 7, this one is asking for you to evaluate the series and find the total number of terms in this series. So for question number 7, we're going to go ahead and take 0 and plug that in. So 3 to the 0 power, 3 to the first, 3 to the second, 3 to the third, and 3 to the fourth. Our upper bound is 4. Okay, well, let's go ahead and solve that. Anything to the 0 power is 1. 3 to the first is 3. 3 squared is 9. 3 cubed is 27. And 3 to the fourth power, you might have to think about it. 3 times 3 times 3 is 27. If you multiply 3 times 27, you'll get 81. All I need to do now is add. So if you were to add up all of those values, you would get 121. That's your answer. Part 2 of this says to find the total number of terms in the series. Okay, well, I'm going to use that special formula that I kind of created down here, where I take the upper bound and the lower bound and then add 1 to it. That's going to make my life a lot easier. Or you can technically add up the values that I have. I'm going to still use my formula, so this is part 1. Part 2 is to find my terms. So I'm going to take 4 minus 0, and then I'm going to add 1. Well, 4 minus 0 is just 4. 4 plus 1 is going to give me 5 terms. There's 1, 2, 3, 4, 5 terms. Pause the video now. Do number 9. For question number 9. For the terms, you should have had 4 squared over 2, 5 squared over 2, 6 squared over 2, and 7 squared over 2. It looks like there's 4 terms. I'm not going to write my final answer just yet, but I'll at least think about that in my head. I probably have 4 total terms. What I'm going to do from here is I'm going to actually add them. Notice that all of these have a denominator of 2. I could rewrite this as 16 over 2, which will reduce to 8. But instead of doing that, I'm going to keep all of these as a denominator of 2, because I know 5 squared is 25, which cannot be divisible by 2. So I'm going to keep all of this over 2, and I'm going to rewrite 16, 25, 36, and 49, because some of those numbers can't reduce right now. I'm going to add up all of my numerator and then divide it by 2. You can actually divide these first and then try to find what your answer is when you simplify it, but I just find this to be a lot easier. So if I was to add 16 plus 25 plus 36 plus 49, I'm going to get 126. And 126 over 2 is just 63. That's my sum. That's my evaluation of my summation symbol. The last part of this, I'm going to take my upper bound and my lower bound and subtract it. And then I'll add 1. 7 minus 4 is 3. 3 plus 1 is 4. There should be 4 terms in this question. Let's look at the last 2 questions. In your last 2 questions, we're going to rewrite your series in sigma notation, which is your summation symbol. That's that little E. And then we're going to look at it with referencing k equals 0 and k equals 1. K equals 0 and k equals 1 is this information down here. So it's your initial or your starting bound, your lower bound. So let's go ahead and look at question number 10. So for question number 10, I kind of want to see what's happening here. I'm going to make a lazy table. Usually I make it nicely, but here's my n, here's my a sub n. Here's 1, 2, 3, 4, 5, and 6. And actually, since it says k equals 0 and k equals 1, let me rewrite this as k. So a sub k and regular k. So obviously, if I'm starting out this here with 1, I'm obviously finding k equals 1 first. So for my sigma notation, if I can write a better sigma, we're going to put k equals 1 for the bottom. Okay, for that k equals 1, let's kind of look at the what's happening here. I have this over 1. I don't know if that helps. If I look in the numerators, all of these numerators are 1. Okay, well, obviously, I'm probably going to have a 1 up there. But if I look at the signs, these signs are changing. Each one is different. Another thing that I notice is all of the denominators are the exact same as the n values. Okay, so that's actually kind of nice. So let me write it as a fraction over some number. So I know for sure in the denominator I have k because all of those numbers in the denominator are the exact same as your k values. The numerator, though, is a little different. Remember, guys, there's several different ways that I can write this. This is just one way. So one of the ways I can write this is I can put the -1 in the numerator. And remember, that -1 is changing every single time. That's why I'm putting that k next to it. That's like what we did earlier. Well, let me think. If I put a 1 here, that's not going to give me the positive symbol that I'm looking for. So with this k in the numerator, or in the exponent's place in the numerator, I need to either add 1 or subtract 1 in order to get it to be a positive or negative value that I need. So for instance, let me plug in 1. 1 plus 1 is going to give me 2. Well, if you have -1 squared, that's going to give me a positive symbol, so that's good. Let's say I had k, which is in this case 1, minus 1. Okay, well, 1 minus 1 is 0. Anything to the 0 power is 1, which means it would turn out positive. So I'm still good. This would be one way to write your answer. Another way you could write your answer, oh, and one other thing you don't want to forget, and I will take off points, and I would have taken points off of my own paper, is the upper bound. Where are we stopping? Well, if we look at all of the k values here, we're stopping at 6. So up here, please don't forget, put that 6. Another way you could write the same value for k equals 1. So k equals 1, don't forget the upper bound, which is 6. Another way you could write this is 1 over k. So we could take that 1 over k like we just saw, and we can take that and we can multiply it by -1 to the k plus or minus 1 power. You don't have to put both of those plus and minus. I'm just telling you that you can pick one or the other. So either put k plus 1 or k minus 1. On your tests and quizzes, don't put both. Okay, there's one last thing I need to find before I can move on to question 11, and that's when k equals 0. Okay, so let me write my summation symbol again. This is k equals 0. And in this case, I'm purposely using a different color because if you have a k, these are going to turn into 0, 1, 2, 3, 4, and 5. So my upper bound is now at 5. If you can't tell, that is a 5. So I need to figure out what the pattern is here. Take a second and look at it. What do you notice could be your pattern for this? Is there a pattern? Well, the good news is, if I was to take this k value, because I notice again that these values are still alternating, positive and negative, if I was to use my negative notation, -1 to the k power, that would work without me having to add or subtract anything, because anything to the 0 power is 1, so that would be a positive. Anything to the -1 to the first power is just negative, so that works. And I can keep doing that all the way down this same row. But what about the actual fractions, though? These fractions aren't the same. Okay, so I'm going to put another parentheses behind this, because remember, there's multiple ways we could do this. In our numerator, the value at the top is not the same. In the denominator, our value also is not the same. For this question, though, this one is the same. Oh, wait, all of the numerators are 1. Oh, that's awesome. So if all of the numerators are 1, I can just put a 1 in the numerator. Whew, forgot about that. For my denominator, though, all of the denominators, I used to just take k because it was the same, but these aren't. If I take 0 and put it down here, I would have to add 1 to get 1. If I had k equals 1, put it in the denominator, I would have to add 1 to get 2. Same thing for 2. If I had 2 in the denominator, I'd have to add 1 to get 3. So let's put a k plus 1 in the denominator to make it equal to our denominators that we want. This is just one way of writing your answer. Another way we could write this, 5, k equals 0. We could rewrite this as -1 to the k power over k plus 1. Either of these, and there's probably a couple other ways you can do this, but make sure when you're writing this summation out that actually works. Does the pattern that you put work? Right now, pause the video and try question 11. Okay, so let's look at what we have. So for right now, I'm going to put this 1 over 1. This is positive. I'm going to make my k. Let's do a sub k, and let's find k for 1, 2, 3, 4, 5. Okay, so we're doing k equals 1 first. So I'm going to do the summation symbol, k equals 1, and it looks like it's going to go up to 5 terms. Okay, let me look at the pattern that I have. There is a pattern, you just have to find it. The first pattern that you should notice is that each of these are switching from positive to negative every single time. So I'm definitely going to have to put that little -1 to the k value, just like we did on the last question. But whenever you're looking at the k, you want to see, is it actually going to give you that sign? So for instance, k to the first power is -1. Negative is not going to give me a positive. So I'm going to have to either add or subtract for each of the k values. I'm not going to put both. I'm not going to put both like I did on the last question. I'm just going to put, we'll say +1 for this one. And you could put -1 if you want to, because either way, it'll give you the same answer. And if you want to double check, 1 + 1 will give you 2. -1 squared is positive. So yes, this will work. And then for the rest of it, I need to see what's happening with these fractions. I have 2/3, because that 1 isn't really helpful. 4/9, 8/27. You've seen these numbers before, so let's think of it this way. If you had 2 to the first power over 3 to the first power, that gives you 2/3. If you had 2 squared over 3 squared, that gives you 4/9. 2 cubed over 3 cubed, that gives you 8/27. And 2 to the 4th over 3 to the 4th will give you 16/81. That's my pattern, guys. You have to take that 2/3 and just change the exponent each time. I do need to make one more little adjustment, though. For my k value, I would need to put, or for not the k value, for 1, I need to make this 2 to the 0 power over 3 to the 0 power. That would give me my 1 that I need. Only thing is, though, if I was to rewrite this here, 2/3, I would need to not just put the k value. I would need to put it as k minus 1. I can't just put k. I would have to do k minus 1. Because for every single number that I'm plugging in, for instance, 0, for instance, 1, 3, that's going to have to work. So in order to make this a little nicer, here's one way you can write it. Another way you could write it, this summation symbol, k equals 1. You could also rewrite this as -2/3. So just combine that -1 with the 2/3 and then make it to the same exponent, which is k minus 1. This would probably be a nicer way of writing it instead of what I put, but it'll still give you the same answer. Now let's look at it for k equals 0. So for k equals 0, we're going to do 0, 1, 2, 3, and 4. So in this question, there's going to be 4 terms. Well, not 4 terms, but my upper bound is 4. And that's when k equals 0. Okay, let's take a second and look at it. I'm only going to write one equation for this, or one summation series for it, notation, so that way you guys have it. Okay, so the same thing happens. We are switching between the negative and the positive. So in this case, though, if we're starting with 0, let me rewrite this as -1 to the k power. If I start with 0, anything to the 0 power is a positive 1. Okay, that works. K to the first power. -1 to the first power is negative. Okay, so that's going to work. My -1 to the k will work. But for the rest of it, though, okay, it's still going to follow the same 2/3 pattern, but if I have k, on the last question, we had to do k minus 1 for each of those. I don't need to take k minus 1 because now I have the exact value that I was looking for. Those are my exact values. So instead of putting k minus 1, we're just going to put, in parentheses, 2/3 raised to the k power. That's my answer. When you're doing these questions, guys, the next several pages of this are just pure practice. And I have the answer keys all worked out nice and pretty for you guys to look at if you need them. So don't just bank on today being the only day that you look at this. Take time to practice these questions over the next several days.